Okay. Eraser. Okay. So determinants. So determinants are very important. Determinants are very important. Um, the determinant of a 2 by 2 matrix is the easiest determinant. So say we have some matrix A that is equal to some numbers as of yet specified, A, B, C, D. Okay. If I want to know the determinant, of A, it's simply equal to, so determinant of A is simply equal to AD minus BC. Okay? AD minus BC. Okay? People with me? I should take a second to just explain why a determinant matters. If a determinant is zero, it means that your matrix doesn't have an inverse. It means that your matrix does not have an inverse. Okay? Which we're going to look at some math. Maybe I'll start it today. I just wanted to look at our timeline. So today is the 18th. So, okay, I might end up being a day behind, but that's okay. So this week is mostly about multiple regression and using matrices to solve for multiple regression. As we'll see, when we want to solve for multiple regression, we need to take an inverse. Okay. I don't know if anybody has any experience with multiple regression. If not, it's okay. That's what I'm here for. Okay. But you will sometimes find that when you ask software to solve for the multiple regression equations, it will say I can't. It will say your matrix is singular. Singular. Okay. A singular matrix is a matrix that has no inverse. Has no inverse. A way to test for a matrix to not have an inverse is to calculate its determinant. If the determinant is zero, there is no inverse. Okay, there is no inverse. There is a generalization of this, but I mean, yeah, we'll just do it really quick. And if somebody's really curious, we can talk about how we get this result. Let's say that we have some B. Say that we have some B matrix that has A, B, C, D, E, F, G, H, I. Okay. If I want to find the determinant of this thing, if I want to find the determinant of B, that's equal to A multiplied by E times I minus FH. Sorry. Minus FH. So A multiplied by this little 2 by 2 determinant down here. Okay. And then minus B multiplied by D times I minus F times G, right? So D multiplied by this little determinant over here, okay? Sorry, I covered up the wrong thing. I meant B. B multiplied by this determinant that excludes it, so it's got D and I and F and G. Okay, so it excludes that stuff, right? So I can't quite get my hand in the right position. Right? So it's B multiplied by the 2 by 2 matrix that doesn't include that column. Okay. Then plus C multiplied by, and following those same patterns, D times H minus E times G. Okay. Right. So C multiplied by that little 2 by 2 determinant. Okay. Right. So don't stress. Like I'm not expecting you to memorize that. I just want you to be aware that this is a solvable thing. Okay, there's a pattern here. Okay. I know I can't get the projector to work, which is really sad. I wonder. I'd really like to show you guys how to do some of this stuff in R. If I can't do the projected order, it's going to be painful. So maybe I'll start the next topic. I'll start the next board topic, and then I'll pray that we have technology next time. Okay? Everybody cool with what I've done so far?
Yeah.
So again, determinants are useful because we can use them from the get-go to find out if our matrix has an inverse. Okay. So there's this idea, another word that you will hear out there in the universe. Okay, again, this is the Cliff Notes version of a lot of important data science topics. Okay, but there's a word out there called multi-collinearity. Let's just start with collinearity. Okay, collinearity. Collinearity means that at least one row in your matrix, is actually just a combination of other rows in your matrix. Okay, it's actually just a combination of other rows in your matrix, such that you could basically eliminate an entire row without losing any information, because it's just a combination of other rows that exist in your data. Okay. When that happens, you can no longer find the inverse, because which row are you going to zero out? Well, it's undetermined. It's undetermined. Okay. So this is what we call collinearity. It most often happens in multiple regression when we accidentally put the same variable in twice. Okay. That matters because if you put the same variable in twice, then of course two rows are a linear combination of each other, right? Does that make sense? So this happens by accident. Sometimes people measure things and they think that they're different variables, but they're actually the same variable. Okay. And it's important to note that, computers are doing things numerically. So sometimes if your variables aren't quite the exact same thing, but they're incredibly close, like you measure IQ with, a slightly different form than IQ on another form, right? If those things correlate at like 0.99, even though they're not perfect, your computer might still blow up because it might numerically estimate the determinant to be 0, right? They might be doing a bunch of stuff and it'll be like, no, I can't, right? I give up, right? Anyways, I'm getting a little too deep in the weeds, but the point is, and actually this will help to illustrate it. The point is, yeah, I gotta write some stuff. So everything we learned about, was everybody here for the linear regression part? Is anybody not here for the linear regression part?
I wasn't, but I watched the video.
You were able to watch that one?
Yeah, it was the YouTube link one.
I did link it.
Yeah,
I'm a good person.
yeah. So I went through
Okay.
that.
Okay. That should have been good, I hope, because that was me at my best. I put time out of my day to record that. So. Okay, so we're all up on that. We're all up on how that all makes sense. Linear regression uses what we call the sum of squared errors. We try and minimize the sum of the squared errors, right? Okay, everybody's with me on that? Mm-hmm. Okay, so multiple regression. Multiple regression is the next step in linear regression. Okay, so in linear regression, you had an equation that looked like this. Y I hat is equal to beta naught multiplied by, I meant beta naught plus beta 1 multiplied by x1, right? Mm-hmm. That was your entire deal. Agreed? Mm-hmm. Okay. Now, what if, I'll write this in a different color. What if I now have a second x squared? Right? So think about this. And there's a reason that I gave you all that homework assignment where I said, what variables do you think might predict children's heights? Yeah. Right? This is going to come back full circle. Okay, not today, but it will. So, if you're trying to predict children's heights, you could create a bivariate model, right? Where your outcome, where the y variable is children's heights, you could create that model. And you could say, I think it's predicted by the father's height. Okay, that's one model. You're done. You've run out of variables, right? You put in father's height for x1, right? We're just looking at the blue model here. You put in father's height for x1, you're done. That's all you can include in your model. But we know that we would like to include other things that probably explain additional stuff, like the mother's height, like the child's age, right? What else do we have? Like the child's gender, right? We may have had a few others. How do we do that? This is how, right? We build a bigger model, right? So we can have multiple independent variables. So this is B3, X3, right? Plus dot, dot, dot. And we will have however many beta values and X values necessary for however many inputs we have. For a good reason here, I'll call this beta P plus 1 multiplied by X P plus 1. We'll see why in just a moment. Okay. So we could build a giant model. And to do that, to do the math that would let us do this, hopefully everybody can appreciate the fact that as we add more terms, we could get better and better explanations, better and better predictions. Okay. To do this math, we need to now move into linear algebra because we have multiple variables all going on at the same time. We have to solve for them one by one. So we're now going to have a vector of y values. We're now going to have a vector of that vector will have the first person's y value, the second person's y value, dot, 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 down to the nth person's y value. Okay? This is a n by 1 matrix, an n by 1 matrix, okay, known as a column vector. People cool with that? Okay. We are also going to have something called an X matrix. Okay. This is my predictors. These are my predictors. Okay. So my X matrix is going to have, let's write it like this. It's going to have a row. It's going to have a row for each person. So let's say, we'll just do it like this. And it's going to have columns. For each, sorry, I wrote that funny. It's going to have columns for each predictor variable. Okay. I'll actually come back to X in a second because let's talk about the predictor variables. Okay. We are going to have a vector. Of predictors. Right? Mother's height, father's height, child, age, right? On and on, right? This is going to be a vector where we have beta naught as our first element. We have beta 1 as our second element, right? Beta 2, dot, 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 beta, and again, we'll see why I'm doing this. Beta P plus 1. Okay? P plus 1. Just so we're all clear what P plus 1 is here, okay? Let's just think about a model, right? Let's think about a model with 3 predictors, right? Y hat is beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, okay? Let P be the subscript on the last beta. My beta vector is P plus 1 elements long because I have beta naught. Okay, that's why I'm writing P plus 1 up here. Is that cool with everybody? Okay, so sorry, actually this should have just said. That would have worked fine. I didn't need P plus 1 there, but I do need it here. Because I need to make sure that I have enough room for all of my betas. Cool. All right. So this X matrix, we'll see why. But the very first column of this thing is all ones. It's all ones. Actually, I don't need to tell you. I don't need to say, let's see why. I'll tell you why, and we'll see the math play out. Because this beta naught doesn't multiply by an X. It multiplies by a 1. Right? It multiplies by a 1. For that reason, For that reason, the very first column, right? The columns for this, oh man, so sorry, everybody. This is an n by p plus 1. So sorry, everybody. So this enumerates from 1 to ... to n. So sorry about that. I'll let you fix your notes and then I'll continue. If that confused you, I apologize. Okay, so the very first column of this X matrix is the stuff that's going to get multiplied by this p vector for the very first element of the p vector, beta naught. Okay, well that's going to be 1, because beta naught, b naught, sorry, I'm using capital B's and lowercase b's, my notation's awful. Okay, but b naught is not multiplied by an x, it's just multiplied by 1. Whereas beta 1 is multiplied by an x. It is multiplied by an x. Okay. And I should be very, very clear here. Sorry that I haven't been, right? But this is for a particular person. This is for a particular person, right? So that's xi1, xi2, sorry, xi3, right? Because each person is going to have an x1, an x2, an x3, and an x4, and so on and so forth, right? Okay. So what's going on here is for the very first element, right? We can think about that as corresponding to beta naught there. It's just a column of ones. Whereas our second one here, right, the one that corresponds to B1, this is an X value for the first person and the first beta value, B1. This is an X value for the second person and the first beta value, X21, right? This is an X value for the third person and the the beta 1 value, right? ... This is an X value for the nth person and for the first beta value. Okay. Continuing along this row, right? We're going to have one of these for beta 2, ... We're going to have one at the end for beta p. Okay. So this is going to be X for the first person, right? For the second beta. And finally, way over here, ... We're going to have X for the first person and the p beta, right? People with me? Okay. Each person is going to have these, right? They're going to have scores for all of these variables, right? Okay. Right, and I'll write this last one here. This is X and P. All right. So we talked about how in the scalar form, something that we cared a lot about was, right? We cared a whole lot about our error terms, right? Well, let's talk about what our error terms look like here. So now we're going to have a vector. We're going to have a vector of error terms. We're going to have a vector of error terms, and it's going to be equal to the y vector, people's actual y scores, minus x multiplied by b. X multiplied by b. Maybe a demo would be helpful for this. Let's think about, let's just take this to the simplest form. Let's take this to the simplest form so that we can all just sort of see why this works. Okay, so if this is my form, this is my equation, right? Then my X matrix looks like this, right? My X matrix looks like this. I have one. Let's say that we have 2 people. That may not work. Let's say that we have 3 people. Okay, 1, 2, 3. Okay, and let's say that we have these 3 variables, right? So that's beta naught. This is beta 1. Okay, so we have person 1's score on the first one, right? Person 1's score, sorry, person 2's score on the first one, person 3's score on the first one. Okay. Beta 2, right? We have person 1, 2, person 2, 2, and person 3, 2. And that's the X matrix for a multiple regression with 2 predictors. Okay, 2 predictors, thus 3 betas, because beta needs to have an element for beta naught, for beta 1, and for beta 2, right? Okay, let's see what happens when I take x and multiply it by beta. Okay. Well, we'll just go ahead and write it like this. So on the left, I have 1, 1, 1, x 1, 1, x 1, 2. I have x 2, 1, x 2, 2. I have x 3, 1, x 3, 2. Okay. Now I'm going to multiply this by b naught, b1, b2. Okay. So this is a 3 by 3, agreed? And this is a what? Pop quiz. 3 by 1. 3 rows, 1 column. Are they conformable? Conformable means that the number of columns on the left matches the number of rows on the right. They are conformable. What will my result be?
Yeah, 3 by 1.
Yeah, my result is going to be a 3 by 1. Okay, so my result is going to be a 3 by 1, right? Okay, let's look at my very first element. My very first element is going to be this row vector, right? Multiplied by the only column vector there is, right? Okay, so we get 1 multiplied by, sorry, I need to make this a little bigger. We get 1 multiplied by beta naught plus x1, 1 multiplied by beta 1 plus x, I still didn't make it big enough, plus x 1, 2 multiplied by beta 2. Okay, as we should. And if it's not clear why, we'll look at it in just a second once we've cleaned everything up. Okay, now I'm looking at this row vector. I get 1 multiplied by beta naught plus x 2, 1 multiplied by beta 1 plus x 2, 2 multiplied by beta 2. Okay, and finally 1 multiplied, trying to be consistent, 1 multiplied by beta naught plus x 3, 1 multiplied by beta 1 plus x 3, 2 multiplied by beta 2. No, okay, this is my result. This is my result. Okay. Just cleaning this up, this result is beta naught, I'll put it in an order you're familiar with, plus beta 1, x1, 1, plus beta 2, x1, 2, right? Yeah. So far, so good. Okay. The second one is beta naught plus beta 1, x2, 1, plus beta 2, x2, 2, and finally beta naught plus beta 1, x3, 1 plus beta 2, x3, 2. Agreed? Okay. These are my predicted values. These are my predicted values, right? It is literally this equation. It is literally this equation for a particular ith person, right? If you plug in 1 for I, you get the first row of this matrix. Does everybody see that? You plug in 3 for I, you get the third row of this matrix. Okay? So quite literally, x multiplied by the beta vector is my vector of predicted values for all n people in my study, n being 3 in this case. People cool with that? Okay. We just talked about how this is a 3 by 1. Okay. This is a 3 by 1. Sorry, the result is a 3 by 1. I keep pointing to the wrong thing. It's not what I'm trying to look at right now. Let me write this up here so it's not in the way. I'm not changing anything, just writing that there so it's out of my way. So we talked about how this is a 3 by 1, right? Once you actually do that addition, you only have one element to those, right? So it's a 3 by 1, okay? Where 3 was my number of people, right? So in general, x multiplied by the beta vector will be an n by 1. What was my y vector? N by 1, which means that this subtraction is defined. People remember that in subtraction, in matrix form, everything has to be element-wise. So the two matrices need to have the same number of elements, and they do here. Okay? I'm almost out of time. There's one more thing I want to show you, but I'm just pointing out that so far, what we've constructed works. What we've constructed works. This E vector is quite literally equal to the vector of y's minus the vector of predicted values for y. Okay? So this thing, I mean, it has to be, it's going to be the first y value minus the first predicted y value, right? So that's going to be y, let me make sure that my subscripting is good. That's going to be yi minus that giant thing down there, beta naught plus x11 plus, plus beta 1 x11 plus beta 2 x12, right? The second term, sorry, I said yi, that would be y1. The second term will be y2 minus beta naught. Sorry, we got to put all these in parentheses because that's subtraction. Beta naught plus beta 1 x21 plus beta 2 x22, right? And then finally y3 minus beta naught plus 1 x2 or 32 plus 2 x32. Does everybody see how that all comes together? So this is quite literally, as I said, a vector of my predicted values. A vector of my predicted values. I think the last thing we're going to have time for, is to talk about the thing that we care most about, right? Remember, what we actually care about is each of our EI values squared, right? We want to take the residual sum of squares. We want to take the residual sum of squares, right? Where that is equal to the sum from I is equal to 1 to n of my EI values squared, right? That's what I'm trying to get to. Okay. Well, there is a matrix form of that. There is a matrix form of this, okay? And it is simply equal to this. E transpose E. E transpose E, okay? So this is my E vector. This is my E vector, right? I've written it like this, right? For shorthand, we could just say it's a vector of the first error term, the second error term, right? Eventually the nth, but eventually the nth error term, right? Okay. If I take E transpose E, I'll write it way over here because I'm out of room over there. If I take E transpose multiplied by E, what do I get? So E is a what matrix?
It's a I by 1 or
N by 1, right? So E is an n by 1, which means that E transpose must be
1 by n.
Yeah, say 1 by n matrix, right? Say 1 by n matrix, okay? So I'm going to have a 1 by n multiplied by an n by 1, okay? Are these two things conformable? I have a 1 by n multiplied by an n by 1. They're conformable. And what will the result be?
1 by 1.
A 1 by 1, also known as a scalar. Okay, that's good. That's good because the sum of the squared errors should just be one value, right? So at least dimensionally, we're pretty good, right? So this will be equal to, as Josh said, it's a 1 by n. So this will be my first error term, my second error term, dot, 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 my nth error term, right? That is a 1 by n, okay? It'll be multiplied on the right by a n by 1, right? Agreed? This is what we're looking at. And the result will be a 1 by 1. The result will be a 1 by 1, right? Well, let's think about what that result will be. It'll be this first row vector multiplied the dot product by this first column vector, and that'll be it. So it'll be E1 multiplied by E1 plus E2 multiplied by E2, right? Dot, 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 plus En multiplied by En, which quite literally is the sum of the squared errors, right? Okay, so, and yeah, that's where I'm gonna have to end for the day. But the residual sum of squares is quite literally equal to E transpose E. E transpose E. So our job in matrix form will be to try to make E transpose E as small as possible. That will be our job. Right? Okay. How are people feeling? Okay. I'm going to try really hard to get the tech to work so that we don't just play in whiteboard land. It's important, but it's not the be all end all. So hopefully we'll have some R next time. People okay with the homework due tomorrow? I feel like, oh, you did ask a question, Spencer. You're okay?
Yeah.
Okay. All right. Cool. Class dismissed. See you guys on Wednesday.